So in this video, I will start talking about the general form for transformed sine and cosines, the important parameters that we need to keep track and know and memorize. Okay. So here is our general transformed versions of sine and cosine. Let me get the highlighter out again. These two, a times sine of b times x minus c plus d, or change that sign to a cosine. So in terms of transformations, get down the pen. In terms of transformations, A does what? It is vertical stretch or compression and reflection if it's negative. Okay. How about B? It's horizontal stretch or compression. And if it's negative, it's a horizontal reflection as well. What about C? Is a horizontal shift. Yeah. And D is a vertical shift. Remember all those? Okay, those are in terms of transformations. Those can be helpful to help understand these new terminology that we use, like amplitude, frequency, period, those things. But if we think of graphing in terms of these shifting, stretching, reflecting, it's much more difficult. Okay, you'll see when I do one example with the slow way of all these transformations versus the quick way with the new trig parameters. All right. Okay, let me get rid of this now. Okay, so let's talk about the horizontal parameters once more. Actually, let's include that general formula. Okay, so B, as I just said, has to do with horizontal stretch or compression. Okay, if absolute value is less of B is less than 1, it's a stretch. If you remember, absolute value B greater than 1, it's a compression. Okay, so in terms of our new trig terminology, remember period, how long it takes for the function to repeat itself. The period is 2 pi over absolute value b. Okay? So if absolute value of b is less than 1, how does it change t, capital T? The period is longer. You're dividing by a small number, so it gets bigger. Okay? And let's connect it with the transformation. Period is longer and horizontal stretch. Think about it. I won't say it out loud, but I'll give you a little bit to think about it. Okay. And similarly, if absolute value b is greater than 1, again, we look at the formula for capital T. If we're dividing by more, the period is smaller, period is shorter. So think about how that's the same as a horizontal compression. Okay. Now, C, if C is less than 0, we shift to the left. Remember, C greater than 0, we shift to the right. No different in terms of trig terminology, except we call it a phase shift. That's all. That's different. Okay, instead of a general shift, we just typically call it a phase shift. Okay, so again, C less than 0, shift to the left. C greater than 0, shift to the right. Okay. And some additional info. Every teacher is different. You might need to know this. You might not. But the term B in many physics applications is called the angular frequency, not to be confused with just frequency, which was 1 over t. Okay, remember frequency, which is 1 over t. The units are 1 over seconds or hertz. So, this is not right. Actually, my bad. The units of B, not radians per hertz, is radians per second. Where's my pen? See, this is good why I'm doing this. I can fine tune this further. Radians per second. Okay. And the domain doesn't change, negative infinity to infinity. No matter how you shift or stretch, compress, or even reflect, if the original domain was negative infinity to infinity, your final domain doesn't change either. Okay. Now let's talk about the vertical parameters. Okay. Let's review again. A, if absolute value A is greater than 1, we know that's a vertical stretch. If absolute value A is less than 1, that's a vertical compression. Okay. In terms of trig terminology, amplitude is the absolute value of A. Think about it in terms of the definition of amplitude once again. Amplitude is how much it swings up or down from the midline, which I'll go over next. Remember midline? So connect how a bigger amplitude is a vertical stretch in your own mind, okay? You gotta do it for yourself in order for you to fully understand. And even better if you can explain it to someone else, okay? Now, let's move on to D. D, we know that if D is less than 0, is a shift down, and D greater than 0 is a shift up. Okay, D in trig terminology is the midline. Okay, again, connect the dots. Think of how the midline is equivalent to a vertical shift. Okay, and the range, remember, it is midline plus or minus amplitude. So D plus or minus A, which gives us D minus A as the lower bound, D plus A as the upper bound. All right. Okay. Those are the basics that we must know. These are a little more advanced, but can be helpful. Okay. What happens if A is less than 0? What was A again? A had to do with the vertical stretch compress, but remember, in terms of transformations, if A is less than 0, that is a vertical reflection as well. Okay, so that's why I said here, it's a vertical reflection. So that's fine, but we can think of it a little more advanced, actually, because this will help us when we have to model, which will be a separate video. Okay, so let's look at the graph of minus sine x, the dashed one, the dashed blue one, and just regular sine of x, the solid, I believe that's red. Okay. Aren't they just phase shifted versions of each other? And by how much? By half the period. Let's look. Okay. Sine of x is here, right? Where did the starting point shift to? It's here now, right? I'll go on like that, right? How much is this? This is shifted by pi. And what is the period of the original guy, sine of x, or even just negative sine x? And they have the same period. It's 2 pi. So that's the key concept here. If you don't want to deal with a vertical reflection, it is equivalent to a phase shift by half the period. Okay, this is a little more advanced, but this is helpful, especially when you get into modeling. So that's why I'm going over it. Okay. Now, what happens if B is less than 0? Okay, let's actually go back once again. Sorry for the scrolling. What is B? B has to do with the horizontal stretch compressed, but if B is negative, that's a reflection, horizontal reflection, right? Okay, we have to look at the case for sine and cosine individually because a horizontal reflection for each of them is different. Okay, so let's look at sine first. So let's compare the graph of sine of x. So I'm looking at this guy right here. Okay, let's compare the graph of sine of x, a solid one, to sine of negative x, the dashed one. Didn't we just look at this graph, the dashed one? Whoops, I stretched the share display a little bit. That's fine. Okay, we just look at it up here. So notice how notice how sine of negative x is the same as negative sine of x. This dashed curve is the same as the other page, the page above. Okay. This is because sine is an odd function. What is the odd function? Do you remember? Algebraically, f of negative x equals negative f of x. And an odd function graphically, what does that mean? It's a reflection about the origin, if you remember. Okay, so instead of doing a horizontal reflection, we can do a vertical reflection instead for sine of x. Okay, typically vertical things are much easier to do than horizontal things. All right, now let's look at the case for cosine. All right, Cosine of x is the solid one. Cosine of negative x, the reflected version, is the dashed one. Can you kind of see the dashes? Let me zoom in a little bit. It's kind of hard to see, but it's there, right? So what does that mean? They're the same curve. This is because cosine is an even function. And remember algebraically what that means? F of negative x equals f of x. What does it mean graphically? It is a reflection about the y-axis. Okay? Therefore, a horizontal reflection has no effect on cosine. We can actually ignore it. Okay? All right. I believe that's all the things I want to go over in this video. In the next video, I will be going over how to do this example in terms of the old way of transformations, which is much, much slower, versus the new way if we just understand the concepts of amplitude, midline, period, phase shift. That's all we need, those 4 things. Okay? Hopefully you've seen that video. Bye.